Hello everyone, Blair Hall. I work here at MSL, although my colleagues rarely see me these days, thanks to digital technology. I'm also, that's my title, so I'm also involved in a little international group, an Asia Pacific group interested in digital technology for metrology. And so today I just want to give you a bit of a talk about the flavor of it. So the theme, metrology in the digital era, what does that mean? I mean, you've expressed yourself, it's World War II technology, really? Somebody made the comment to me that, what's the big deal? We already use equipment that produces digital data. We suck it up with our computers, we process it in Excel, and we generate our calibration reports in Word. So digital transformation, it's already happened. Well, I have some sympathy with that point of view, but the people who chose the title for today's International World Metrology event were clearly thinking of something different. So in order to give you an idea of what I think it was intended, I thought, well, what's a good example? And I thought, well, international travel has been through its digital transformation. So many of you, I think, will remember when you were traveling overseas, you would be given a ticket. And if you were traveling for a long time, you had to guard that ticket very close to you. I used to carry it in a little pocket around my neck, because if you lost it, you were in deep trouble. And then they transformed to a digital system, and it all became much easier. So I thought, well, this is a good example. Google search, images, digital transformation for travel, but this is what came up. And I think this shows that my expectations were wrong too. So I was thinking about this sort of stuff here, the fact that there is an electronic identifier for me and my ticket and the itinerary that I was going to have. But there's a whole range of services and industries and things that have grown up because the core of international air travel digitalized, and these other things have just grown up around it. So I think it's that picture that the community involved, international metrology community, kind of has in mind. Unfortunately, our quality infrastructures look more like this. Right? We haven't made the change, and so they're essentially paper-based and person-centric. And even if we're generating a PDF instead of a paper report, it's still the old way in terms of structure. So the title of my talk today is inspired by, gets reformatted here, but by this. We've seen from Annette's talk this morning that in metrology we like signing things. So you've got these 5 people, no digital equipment in sight, but they're all signing something, and they're signing a joint statement of intent. Didn't think that was it. A joint statement of intent on the digital transformation in the international scientific and quality infrastructure. So there are 2 infrastructures there. And the intent is to develop an SI digital framework. So, these guys, they don't look particularly interesting. They're all of a certain age. They're all sort of Northern European heritage. They all look pretty happy, but what are they happy about? Well, they represent quite a lot of different communities. We've got the president of the CIPM here for World Metrology. We've got the CEO of the International Science Council. We've got the president of the International Science Committee on Data. We've got the president of a large metrology organization, IMECO, and we've got the president of a large legal metrology organization. So these are representatives of a huge body of people. And what they're suggesting that we do has developed the digital SI framework. Now, it isn't really very clear yet what it is, but it's supposed to enable the kind of transformation that we saw on the slide relating to travel. And it's a layered structure because IT people like layered structures. And at the bottom of it is something called the core SI. And that's going to somehow or other capture what we mean by units, measurement uncertainty, quantity, and so on in a digital form. So nothing could possibly go wrong, could it, right? Units, we've had the most unfortunate experience of the Y2K problem. And although that was kind of solved, it cost a fortune and people did die. You know, there were a few very unfortunate outcomes. The Gimli glider disaster where they got confused between kilograms and pounds and only put half as much fuel in the plane as they were supposed to. Luckily, the pilot was brilliant and managed to land the plane safely. Or the Mars orbiter, where they got the units wrong and the space probe, NASA's space probe crashed. So the point here is that since the 1970s, people have been trying to figure out how to represent units in digital form, and they haven't done it. So it's just not quite that easy. Well, work that I've done with myself and Mark Custer, who'll speak shortly, may address this problem. So we may actually have found a solution. But the way that we think we've approached it is significantly different from everybody else's approach. And that's because we've included concepts from metrology in the solution. What I think impeded everybody else is the way that units and quantities and things are taught to all of our science and engineering and technology students at tertiary level. It's done by physicists, and it usually takes about 10 or 15 minutes in one of the first year lecture courses. And it's all based on conceptual models. Quantities are an idea of how things behave in our world. I mean, they're very, very refined. They're absolutely marvelous models. I don't want to knock anybody about this, but when you go to express these quantities, you're coming over into the domain of metrology. The idea of a unit associated with a number invokes the idea of a measurement scale, and so metrology is involved. And that means that we should be telling our students about traceability, about measurement scales, about measurement error, and we don't. And so those ideas don't go off into the community, science community, and people find it difficult to manage metrological concepts. So now, Rod White will talk a lot more about that shortly. What I'm going to do now is just give you a glimpse of digital transformation in another area, but one that you can relate to. That's the standards area. So there's a thing called ISO Smart, which is being worked on vigorously, and they identify these 5 different levels for their standards documents. So here we are with just basic text. Here we are with a PDF file that might be something generated from Word. And here we are with something at level 2 where the information in the file is somehow organized. There's some sort of semantic key information which is embedded in the file. So a machine can start to make use of it. And then we move on to level 4, where essentially the machines are running everything. Now, this is a process that the information science community gets involved with often. You decompose something into its essential elements, and then you rebuild it again. So you knock it down and build it up. And you have to figure out what the essential bits and pieces are, what the components are of your system. So the standards people are looking for what they call information units. And here you could think of, well, if it were metrology, it might actually be units or quantities or uncertainties, things like that. These are the key concepts that have to be captured. So they break it all down into into a bottle of key concepts, and then they build it all up again using what they call an information model. And that's where you need to be able to describe in a logical way how the different concepts relate to each other. And so that's the task. It's one of the tasks that we're now trying to deal with in international metrology. And the outcome, the standards people think this is going to be brilliant, because you'll be able to get much more out of your standards. You'll be able to get tailor-made standards, standards on the fly, standards developed by a machine, and that sort of thing. So they see this as being the future for their business, and they want to make money out of it. Another way you can look at the signing of that document. Remember, there were two people there who came from the science community, not the metrology community. Well, one of the aspects there is that there's this huge problem in science that results are not reproducible. You can't, a lot of the scientific results that are published turn out to be something that no one else can replicate. And so I've stumbled across this listening to somebody else's presentation about this problem. There's a guy, George Akerlof, who won the Nobel Prize for Economics, but he's written this lovely paper called A Market for Lemons, where he describes, using the example of a market for cars, brand new cars, used cars, that sort of thing. He explains the dynamics of the market. And it applies to this problem of science, because when you are the producer of a scientific result, you have all this information about what you did to get it, all of the raw data, the things you threw out, all the tricks that you did, and you finally publish a paper. The person that reviews the paper doesn't have the same amount of information. There's a huge information imbalance, asymmetry. So one of the ways that's been suggested to counter this is, of course, to embrace open science, where everything you do is made available. And so the open science community, who are signing that document, are really interested in finding representations for the data so that it can be shared more widely. Well, I think there's an opportunity here for metrology for open science to take a leaf or two out of metrology's playbook, because the problem of reproducibility, we just don't have it, right? The measurements that we make are trustworthy, or we've done it wrong. So metrology doesn't have the problem that the rest of the science community does. And so as we both go towards a digital transformation, we can share information. So what we have to do is to somehow or other find a digital representation for traceability. And as Annette said, the people that we really want to benefit are down here, the people who are making decisions of their own. But we're up here, the National Metrology, or some of you are here in the calibration laboratories, and we're all in our own little worlds. And what we call traceability is just a stamp of approval. It's just an endorsement, but it doesn't actually provide an ability to trace back the way traceability is used in other industries. So you can't do a recall or something like that without traceability. So to be a little bit more specific, we can imagine a scenario like this. Measurements are performed at a national lab and then reported to a calibration lab, and then finally some piece of kit is used to make a measurement. Now, it's a collaborative process. We all work together to provide people down here with what they need. But what we do at the moment is we just keep all of the information in our little silos and report across those dotted lines, absolute bare minimum. So that's something that really has to change, and that's and how we manage to get more information across here is really interesting. And the other thing is, of course, how do we increase trust by making the quality of the work that's done at these different levels? How do we make that visible to people? So to sum up, I think that we're building a new infrastructure here. The digital infrastructure is going to be there for some time to come. We should build it on scientific knowledge, not on the nearest technology that we think is available to us. The benefits should accrue to the end users. We have to